Hi, so I'm Alex, and this is going to be my Module 3. I couldn't quite figure out how to insert the hand notes, so let me go ahead and press play.
So these are the handwritten calculations, and I took the last module, the covariance and variances of those, and used that bivariate and
Okay, perfect. So let me go ahead and get started with the actual module. So we're going to be focused on the general linear model. And as I said, the general linear model, let's go ahead and keep that in mind because we want to make sure that this equation that we're using is linear. Now, this equation right here is the one that we use for the GLM, and all of those, I guess, variables, but they're not really variables, I guess, parts of the equation. These are exactly what they stand for. So y is a dependent variable, b naught is the intercept, where y equals 0, x is the predictor or our variables. You can have multiple of those, and b is the weight that we associate to those predictors, and e is our residual, or it's called error. We can break down the general linear model into MRC or ANOVA. And I'm going to start with MRC, so multiple regression and correlation. And that's going to use exactly what we're saying. We're looking at correlations and we're looking at regressions. And of course, as with anything, we have to start off with some assumptions. Now, we went over about 9 assumptions in class, but for right now, I'm going to capitalize on rectilinear and homoscedasticity. We want to, like I said before in the a slide before, we want to make sure that our equation and then that our data is more linear. We want to make sure that it's going in more of a straight pattern than kind of all over the place or squiggles or anything like that. And homoscedasticity, I'll get into that a lot more. Here is an example of the factors. Well, not factors, but these would be called variables right now. The variables that I decided to use or the predictors, and for my MRC I decided to use x1, x4, and x7. No real reason why I chose those, I just decided to choose those, and I was going against y2 as my dependent. These are just my correlations, and as you can see, the correlations aren't looking too good for any of them really, as well as any of the interactions. But I'll go ahead and get more into that as we keep going. So the MRC continued. Here you can see in this one, actually, I kind of did like a good thing, where here I first ran my MRC only using these predictors, and I didn't take into account the interactions. And so with these predictors, you can see that my betas and my standards of errors, my t-values, and my significant values, really, it's not looking too good for the home team. The main effects, they're really not producing any significant data. My t-values are low, which is going to give me really high p-values. And of course, that means if we have high p-values, then we fail to reject the null. But let's take a look at the VIF, and here you can see that my predictors, they don't have too high of a VIF. Actually, it's not really high at all. So I guess I could say that it doesn't really influence, my standard error too bad, but one really never knows. And here's my r and my r squared. And as we know from previous times, r kind of shows the direction in which we're going and a little bit about the strength. And then the r squared definitely talks about our coefficient of determination and the relationship between my variables. And yes, if you're thinking you get r squared from r, you are completely right. That is true. So remember when I was talking about how I didn't do my interactions to begin with? Well, on this second one, I did actually run the MRC with my interactions, and you can see that there's a bit of the difference between the B's, the standard errors, the T's, and the significant values. They all about doubled. but still I didn't have any significance in any of them. So I guess it would be right now safe to say that there may be some issues with my data, or the factors that I decided to use didn't really show too much. So here is a plot that I decided to do, and it is going to look at homoscedasticity and the residual. These are the standardized residuals and the standardized predicted values. We want to make sure that we use those standardized there. And so as you can see, my variables, they're not really too all over the place. We have some outliers down here and above, but for the most part, I would say homoscedasticity isn't an issue. We want it to be as tight to this green line as possible. You can definitely see that I kind of go out of it, but not too much. But we also want to take a look into that and see, well, okay, are these outliers doing a lot more than we think that they are, or like what's really going on here? So here's my QQ plot, and remember when I was talking about that homoscedasticity, we want to see how around this line of best fit my data seems to go about. And as you can see, it's not too bad. Like I said, there are some areas that deviate a little bit, but you know, it's not too much of a S-shaped curve or anything like that to where I should be too worried. Okay, and here I believe that it's pronounced lows. That is the green line, and I am using this leverage to kind of see those outliers. How like much do they pull my data to one side or the other? And as you can see, my green line isn't too bad associated with the mean that I have right here of just 0, 0, where everything equals 0, and it doesn't pull too bad, but it is definitely pulling a little bit, so that lets me know that perhaps my outliers that you do see, especially this one at the top and this one at the bottom, it could be, you know, skewing my data a little bit. Okay, so what's my point with MRC? Okay, with my data, it's really not looking too hot. There wasn't any significant main effects or interactions. So is there a problem with multicollinearity? I don't know if I would say it's necessarily a problem, but if we go back here and we look, I did have low t values and elevated p values, but over here it's not really saying that they influence too much. So I mean, there could be slightly a problem with it, but not too much. With heteroscedasticity and homoscedasticity, we can definitely see that my graphs here and here, there was a little bit of variation, but it's not as all over the places as it could be, and we don't want it to be all over the place. So am I saying that I need better predictors? Most definitely. I definitely need better predictors. So let's go ahead and shoot over to ANOVA, the other side. What's ANOVA? So ANOVA, as we've been told in class, is more or less like the I guess I would say it's more like the parents out of the group. So MRC is like the cool aunt or the uncle, and then ANOVA is like the parents. It's real strict. So we want to make sure with ANOVAs that this is a measure of difference using factors. And we are looking for the variance between factors. So remember that word variance, we talked about variance a lot throughout the semester. And so we are looking at variances here, but we are using F and T values. So we want our measures to be independent, And the factors that I chose were just one for ANOVA, just as I chose predictors last time. In MRC, I chose F1 and F7. F1 has 2 levels and F7 has 2 levels, but those are within F1. So I decided to use a type 1 sum squares when I was running my ANOVA. And the reason I did that is because in SPSS, the direct setting is to be sums of squares is a type 3, and I didn't want to use that. So is my design balanced? Well, I mean, it's not too bad, but it's not completely balanced, and that could present a problem with ANOVA, especially if you don't have that balance. We really want to try to get as balanced as possible, but I don't stray too bad. Okay, so as I mentioned before, I will be using F1 and F7, and as well as a dependent variable of Y2, same as with MRC, I am using Y2 here. And as you can see with my main effects and my interactions right here, there is, yet again, no significance. Looking at the F-value ratio of variances, you take the mean square and you divide that by mean square, and you divide that by the error or the residual. So pretty much in order to find F, I took this number, well, for F1, I took 0.042 and I divided it by this error right here. And that's how I was able to get my F value. And so I did that for F1, F7, and the interaction. The F value of, let's just choose F7. The F value of this is associated with 1 degree of freedom over, I believe it's 29. Yeah, 29. Sorry. And so that accounts for the residual as well. Of course, this is also at the 0.05 level of significance, and as I said earlier, there really isn't any. Oh, I'm sorry, I misspoke. It was actually 26 for the degree of freedom. We can actually look at the Levene's test to observe homogeneity. Excuse me. As you can see, it's a sad story. Significance is not good. It's not as bad as my MRC, but it's definitely not good, and I failed to reject the null either way it goes. So, yeah, not looking good for the factors that I chose. And as you can see, as I did with MRC, I did the same thing with ANOVA. There is some slight deviation, definitely more towards the top of my graph, but top of my plot, but it's not too bad, and it's not a bad S shape. Okay, and with the ANOVA, I ran an independence of residual. And they aren't as tight or as straight as they could be, especially to this red line, but they're not, again, it's not too bad. The green line is also, I decided to do a los, I believe that's how you pronounce it. I hope I'm pronouncing it right. And it's not too bad. Now, we do definitely have some definite outliers here that definitely skewed my results and this graph, but like I said, it's not too bad. At least it's not wonky and all over the place. But there is some questions of problem with homoscedasticity. And here we talk about my outlier influence, how influential, just as with MRC, were my outliers, how bad were they, did they skew my data? And as you can see, you see those outliers that you have seen this whole time that are just out there chilling. Yeah, they kind of like interfered with my data, but not too bad, but we definitely see a lot more in this one than we did in the MRC. Okay, so the implications of ANOVA are predictors. Well, for this one, it would be factors of ANOVA were not significant for either the main effects or the interaction. Our design wasn't necessarily unbalanced, but it should definitely be more balanced. Perhaps that's like where we went wrong because, as we talked about earlier, there was no real evidence of hardcore violation of multicollinearity or a violation of homoscedasticity, but it could just possibly be that the factors that I chose for both my MRC and my ANOVA just are not significant and they do not, work with my dependent variable. And so, winner or loser between the two, especially with my data, neither the MRC or the ANOVA resulted in anything that we would celebrate for. So neither one of them really worked out for the data that I chose. But like I said, it was just, chosen from the lineup, and it's not really to say that either one of those are bad, but it could be that my factors are just not good factors. Normally, if my variables weren't so messed up, MRC is a bit more flexible than the ANOVA. Like I said before, with the ANOVA, you have a little bit more assumptions. It's definitely more strict. It doesn't internet. It accounts for less when you have more factors. And the MRC, like I said, is just way more flexible. So that's pretty much all that I have for this module. I hope that it helped a little bit. And yeah.